So good morning. I am Krishna Kumar from Krishna's classroom. We begin with another episode of analysis on RNA. Let us recall what we did last time. We introduced the concept of derivative. In fact, what we did was we had a hard look at the concept of derivative in one dimension, namely functions defined on open subsets of real line, and then we found that the same idea works in many contexts. Like you can generalize it to derivative of complex valued functions of a complex variable. He also elaborated the reasons why it worked. And then we can even stretch beyond and go to functions of functions of a single variable, but possibly vector valued functions. Further, we also looked at functions of several variables, and in that case, if we are only interested in the partial derivatives, that means derivatives along the coordinate axis, keeping the function fixed as with respect to the other variables. In that case, one can pursue the same definition. You can extend it beyond that and go to what are called along any line segment. We can talk about the derivative of functions of several variables. That is also possible. There is no difficulty because everywhere, division by a scalar appears, and then the limiting process. So that really works. When we found that if we were to generalize this idea to functions of several variables and define in the generality what is called the derivative, not along any curve or anything, in that case there is a problem because division by vectors are involved, and therefore one cannot directly make use of the earlier definition. So that was the point where we stopped, and in that case we found a way out. The way out was that have a hard look at the concept of derivative. Then we discovered that in the one-dimensional case, it essentially amounted to defining a linear transformation on the one-dimensional space. So that was a breakthrough in some sense because you could generalize this version. And we found that we could define the derivative as a linear transformation from Rn to R. So let us start. So we have a function here defined from omega contained in Rn. We assume sufficient smoothness. Take a point x0 belonging to omega. We said that f is differentiable at x equal to x naught if here exists a linear transformation A or A belonging to such that minus is of small order of small, or if it's not minus AH equal to RH, where RH now H belongs to okay. And A essentially depends on X naught. So A is and we call A and denote it by F derivative. This is the concept of derivative. And you know that in one dimension, this is exactly the case because this emerges as a number, and that number determines a linear transformation uniquely. Such A is determined unique. And this is what we did so far. Now let us look at some examples of functions of several variables, which will give an indication that dealing with functions of several variables involves or requires some caution. It doesn't, things do not appear on the surface very clearly what it actually conceals, and there are a lot of surprises that you would have while working on functions as well. So we start with some examples. First example, we take omega to be equal to, then f is 1, are defined by this is equal to 0. This is the definition of the function. It is like that. Where x and y are the variables in R. Now we make some observations. The first observation is that f is bounded. This follows from the following fact that mod f of x y is equal to for xy in R2 less than or equal to twice mod x y square divided by 4. And one can prove that this is less than or equal to 1. Now this follows from the following fact that so this is a consequence of the following behavior. This follows from the fact that O square, which is less than or equal to, and this implies so that is pretty simple because at origin it is 0 anyway, but elsewhere it is this, and this is the estimated. Now we observe that f is continuous, is not zero. Now you see that, the continuity is something that we have to look at hard here, because you see that, this is R2 and this is the point 0, 0. Now you see that you have to look at whether the function is continuous along all sorts of paths that go here, something like this, or even something like this, radial directions or anything. Okay. Now you see that along certain paths it is continuous. For instance, when along the line y equal to 0, that is along the x-axis, this is y equal to 0, you see that the function is continuous because the function takes the value 0 all along this x-axis. Here also it takes the value x-axis, along x-axis. Now what happens along a radial line, something like y equal to mx? Now you can look at this, put y equal to mx here and look at what happens along that line. Now you see that if you can show that along some path which in the limit goes to the point 0, okay, as t tends to 0, then if you can show that the function is not continuous along that, then the function fails to be continuous because it has to be continuous for all sorts of paths that go to 0. So let us choose the following. Consider the x equal to y square is geometrically the following. Now you see that as x tends to 0, x comma y passes to the point 0, 0. Say y is so y is now let us investigate this. So you will find f of y is equal to what is the function that you have? Xy square divided by x square plus x square. So you get y to the power 4 divided by zero. Now you see that this is equal to 1 by 2. Therefore, limit this is equal to, because it's a constant, does not depend on y at all. Okay, that is limit of f of r which is not equal to, therefore along this path f is not continuous. Now note that on several paths f could be continuous. Notably, along the x-axis and along the y-axis, f is continuous by definition. That's very simple to see. However, it does not mean that it is continuous along all other paths. Okay? You can check what happens along the radial line. We'll have a look at this. Now, we also prove that f is continuous along every straight line passing through the order. That is along all radial lines. This is quite easy. See, I mean, there are, if you take the radial lines, this is y-axis. Now you have the x-axis and y-axis, and this is any general y equal to x. And y-axis, along y-axis, we have to do it separately because y-axis cannot be written as ys equal to fx. Along y-axis, you see that x equal to, then what happens? F of x, y, which is equal to xy square, because you are putting x equal to 0, it is 0. Hence, as y tends to 0, therefore it is continuous along the y-axis. Now let us take y equal to x. So this together it takes care of all the lines. So this is a general line. Therefore, you see that f of equal to x m square divided by square. So for x naught for x naught equal to 0, this is what it comes out to be, and you see that as x tends to 0, as at limit tends to 0 as is equal to that is all variables now remember at other points there is no problem. At other points xy there is absolutely no problem at all. This is a well-defined function. The numerator is a polynomial, the denominator is a polynomial. They are all nice functions, and the denominator does not vanish at other points, and therefore the ratio is a continuous function. So continuity at all other points is there. All points. Being the ratio of polynomials, and the denominator is a polynomial that does not vanish anywhere except at 0. That's the reason. Therefore, you see, we have made an investigation of a function. So we found that the observation is this: along all radial lines, the function is continuous at 0. In spite of that, you see that the function is not continuous because there are certain paths along which the function fails to be continuous. So there is lot of things concealed with the function, so one has to be fairly careful while dealing with functions of several. Now let's take a second. We define again a similar example: xy square divided by x square plus 1 to the power 6 0, and this is equal to 0. That's a definition. Now let us see what happens in this case. Now we can observe that at all points other than 0, 0, everything is nice. Because they are the ratios of polynomials and the denominator does not vanish at all. So you see that they are smooth functions, and therefore the ratio is also smooth everywhere except at 0, 0. So that is the only place where we have to check what happens. Now one also observes that G is continuous along all radial lines passing through zero, 0 at 0, 0. That is rather straightforward to define. And you see that once again, you can check as we did in the previous case along x equal to 0, g x y is equal to 0. Therefore, as y tends to 0, that is taken care of. It is straightforward. This is the line x equal to. Now on any radial line, we have g of four, and you see that this goes to 0 as therefore all radial lines. That is pretty straightforward. Now, unlike the function f, g is unbounded. in every neighborhood of Q. Now to prove this, what one does is suppose we want to show that if you take a neighborhood of 0, 0, we want to show that G is not bounded there. Now you know that at 0, 0 it is defined as 0, elsewhere it is defined as a ratio of two polynomials. Now to show that it is unbounded, it is enough to show that there is some path along which the function remains unbounded. Okay? So that you cannot claim the function is bounded in the entire neighborhood. So let us do that. So for that, what one does is we take the curve now you see that this is the point. Now this is the curve that we are looking at. Then G of this is equal to 1 upon and you see that as hence gxy is unbounded along the curve x equal to by q therefore the function becomes unbounded. So that's about the function g. Again, such nice looking functions become having very strange properties at certain points. So when you deal with functions of several variables, you need not take these for granted. One needs a very thorough investigation of the properties of the function at possible points where you have when you expect some problems. When here, because being ratios of two polynomials in x and y, and the denominator is not vanishing, at all other points there is no difficulty at all. The function is continuous, smooth, and everything. So if you take a point xy which is not equal to not 0 0, and take a neighborhood of that which does not include 0 0, then the function is bounded. It's only in the neighborhood of 0 0 you encounter some trouble. Okay. So even the radial lines, everything is fine, does not really help you to conclude that the function is a continuous function or the function is a bounded function. Or these kind of things cannot be concluded just by looking at the function along the radial function. So it's a deception that you may have, that if you take the radial lines and investigate what happens to the function, that would give you information about the behavior of the function in the neighborhood of 0 0. That is not enough. This is important. Third example, we take omega to be equal to r again, and f is defined from r2 to r by f of xy xy divided by square and f of this is the definition. Now the first thing that you observe is that df by dy, the partial derivatives, exist except possibly why it happens? Because you see that the function f of xy is xy divided by x square minus y square, and if you try to compute the derivative, now you see that the partial derivative means what? The partial derivative of f with respect to x means you are keeping y fixed and then looking at the change of rate of change of f as a function of x. So you can compute the derivative treating y as a constant. If you do that, then you see that it's easy to compute. What comes in the denominator is x square plus y square to the power square, and the numerator, and then you can write down you can compute the derivative. You compute the derivative, there is a polynomial in the numerator, and a polynomial in the denominator which turns out to be x square plus y square whole square, and that does not vanish as long as you keep away from the origin. Okay, so the denominator is not never vanishing. It's a ratio of 2.1. You see that smoothness of the numerator and the denominator takes care of it. Similarly, the partial derivative with respect to y, same argument. It's also quite easy to see. Now we have to see what happens at 0, 0. Now we see that at 0, 0, f of 0, which implies that is, we are trying to work out along the directions x-axis and y-axis. So yes, 0, 0 along y axis, along x axis or y axis. What is the function? F along y axis x equal to 0. So you have along x axis, x is the only variable. This is 0, which implies tends to 0. That's because this is 0, this is also 0. So similarly, this is also important. Or you can even directly compute the derivative. You have x square plus y square whole square, and you have the derivative compute. So you get evaluate it at 0, 0. So you can easily work it out. Therefore, df by dx then df by dy exists everywhere. Because we specifically checked these points, other points there is nothing to check. Therefore, you see that both the partial derivatives do exist. Okay? There is no difficulty about the existence of the partial derivatives. Nevertheless, what we are going to say is that f is not, although f is not a frequency. 0, 0. How do you prove that? It's quite easy to do. Take consider the radial line. Then x squared, which goes to hence as x tends to 0 is equal to x line 0. Therefore, the function is not continuous. Therefore, you see that it's even more surprising that the partial derivatives may exist everywhere, nevertheless, the function may not be continuous at some points. So, this is really startling. Okay? Therefore, we infer that the partial derivatives, the existence of partial derivatives do not in general imply that the function is because we feel that from our experience of working on one-dimensional case, we know that if the function is continuous, if the function is differentiable, then the function is continuous. So here, the continuity along certain directions can be assured, but the continuity of the function as such at the point 0, 0 cannot be assured. That's an example. It's a very interesting example. Here the fourth example. All these examples do give some insight into the problems that we are facing. Or the derivative that we have defined is an altogether different concept. Okay. And we shall soon link up the derivative whenever it exists with the partial derivatives. That we shall do. Let's look at the following problem. Omega equal to r square. Again, defined by now we investigate whether this function is differentiable at the point 0, 0. So we investigate. This function is differentiable. Now, differentiable in the sense in which we have defined the derivative, that means there exists a linear operator or linear transformation from R2 to R such that the relation holds. So, this is what we are. But before that, we look at the derivative along all radial directions. Again, we consider along radial directions. So let us take a vector h. This is the vector h. Now you see that th is any point on this is h. Vector is a vector. H is a vector. Now consider x, y. H1, H2, where you have h not equal to 0, so h1 square plus h2 square. Therefore, f of h2 or what you call f of ht is now computes as h1 to the power 5 e to the power 5 divided by h2 minus now we look at the derivative of this. So let us take f and we take t times log h. Doesn't matter. So limit you can take h to the norm of h equal to 1. And then you see that this is exactly equal to limit of 1 by t four. You can show that as t tends to 0, this is equal to, that's very easy, some cancellations take place. Therefore, if at all the function is differentiable, therefore if at all the function is differentiable, at 0, 0, then f derivative at 0, 0 should be equal to 0 always. Zero. Okay. But now you see that along the curve y equal to x square along the curve y equal to x square, we see that f of xx square is equal to y equal to x square. So this term moves x to the power 5 divided by x to the power 4. So this is equal to x to the power 5 divided by hence, and this is equal to x. Hence, as x tends to 0, and this is not. So the function, the directional derivative or the derivative computed along this curve is not equal to 0. Therefore, you see that the function is not differentiable. So these are some of the examples which throw some insight into the kind of problems that we encounter. The function is differentiable along every line passing through the origin. However, the function is not differentiable along some other curves which pass through the origin. And if it is differentiable in the sense in which we have defined the derivative, that is the derivative appearing as a linear transformation from R2 to R, then in that case it should be differentiable along all the paths that you can take through 0, 0. That is not happening. Okay? Therefore, the function is not, and the derivative should remain the same. No matter what path you choose to compute the derivative, it should remain the same. But that doesn't happen, therefore the function is not differentiable, although the derivatives along all radial directions do exist. Okay. So I think that's a nice place to stop, and perhaps I can make some geometric remark next time on the concept, and then prove some very standard theorems. Okay, thank you very much.